So in this video, we're going to talk about how we can determine the direction of an induced current. If we move a magnet towards it, we create a current, but which way does it go? And then we'll also talk about Faraday's law, maybe not in this order. We might start with Faraday's and then get to the induced current. So you watched a video, and in it, they were dropping down. You know what, actually, yeah, we're going to start with this one. This is called Lenz's law. And this will determine the direction of the current. And so in the video that you watched, he dropped a magnet down into a coil, which induced a current in the coil. And then it was going back and forth, and it went over to another one. But just what I want to think about is, we induce a current in this coil in one of these directions. But we remember that if a wire has a current, then the wire generates a magnetic field. And so let me use two different colors. So the magnet itself is kind of producing some magnetic field, something like this. And then the wire, once it has some current, is going to generate its own magnetic field. And so there's two options using the right-hand rule. One is that it's going to go in this direction. This is basically a solenoid. So it's going to go in this direction, or it's going to go of course, in the opposite direction, depending on the current flow. And then let's think about what the ramifications of this are. So in one case, it's flowing one way, and the other one the other way. That sounded dumb. Okay, so let's think about what this means. Okay, so if the magnet started dropping, let's think about this one first. So if the magnet started dropping, induced a current, and the current induced a field that's in the same direction, well, this magnet would get sucked in. So as it got pulled down faster and faster, the field generated by the coil would get stronger and stronger, and this magnet would shoot out the other end. And we don't see that. So it's easier to see if you just do it by hand. If you hold a magnet and start bringing it towards the coil doesn't grab it and shoot it through. That would be cool if it did, but it doesn't. So just from observations, we might be able to guess that it actually is going in the opposite direction. And that is the case. So this one is true, this one is not for this case. And then based on that, we can figure out which direction the current is, because now we know the direction of the field. So using the right-hand rule, let's see, the fingers would curl this way, so the current is going this way. So the current is going kind of down this way, which generates a magnetic field. This is Lenz's law. So Lenz's law says that the direction of we call this field over here, this B field, this is going to be called the B induced. That's the induced field. And it comes from the induced current, so the induced B field. And Lenz's law just says that the induced B field, so B induced, opposes the change in flux. So basically, it doesn't want to change. So what it does is coming down, since the flux is increasing, it's going to work to push against it. And then when the magnet's going the other direction, so when the magnet's going up, the flux is decreasing. So the B field is actually going to flip, and so the whole current would change direction. So this up and down motion, we end up getting a current that goes back and forth. We get an alternating current. And it just has to do with the amount of B field lines that are being created. That will determine the induced B field. Okay, so let's just look at this one. So we have a magnet, and we can think about initial. So here's my initial position, and then we're going to take it off to a position about like this. Okay, so south, north. Okay, I'm going to draw these B field lines are going to be in green. So we can see that they're going to kind of spread out like that. Let's just draw two of them. And then as I get closer, what's going to happen is they're going to be more dense. So I actually would get more. So I can see I went from, a few to a lot more. So my induced field has to oppose that. It has to take it away. It wants to keep things the same. So like these extra 2, it wants to kill those. So your induced field would be in this direction. That would be your B induced. And then based on that, we could use the right-hand rule, and so we know the current is going this way. That's the current. And then, whether this is positive or negative would determine the EMF. That's what we're going to get to with Faraday's law. Okay, so what happens if you move out? So same situation. Let me scooch down a little bit. Same situation, but now we're going to move out. So we start here, and we're going to move it to over here. Now I'm going to exaggerate. So over here we get a whole bunch of B field lines going through this thing, and from over here, not so many, because they're going to miss. They're going to curl away. So we might get 1 or 2. So we can see that the B field has decreased. So the induced is going to try to add those back in. It wants to keep everything the same. It wants to keep balance. So my B induced is going to be this direction. B induced. And then, so based on the right-hand rule, this is like, I'm not drawing these very well, so I don't know if that was clear with the right-hand rule. So this would go in the opposite direction, my eye. So can we generalize Lenz's law? If, I guess we could say, we'll have to test this out. If the change in flux is greater than 0, so that means that it's increasing, then the B field induced is against motion. I don't know if that's spelled right. Against the motion. And if the change in flux is less than 0, so that means that you go from a big to a small, because it's going to be flux final minus flux initial. So if the change is less than 0, that means that the initial is bigger than the final. So it's getting smaller. Then, oh, you know what? It's always against motion, isn't it? I did terrible on this video. Sorry. No, this one was against motion. Yeah, it's always against motion. Forget all this. I was trying to come up with a general rule. I've never thought about it. I always just think of the flux, how the flux is changing. But it appears as though, it looks like it's always going to be, I don't want to say always, but like we're moving away, so the B is against the motion. We move in, the B is against it. What if we were on the south end? I don't think it would matter. Okay, so we'll work with that. We'll see if that works out. If it doesn't, let me know. I wanted to show you, this is going to get into Faraday's, but here's the idea. So as I move closer, you can see that the number of lines, so I have 2 and I'm going to go to 4 here. So I had a change in flux and it increased. So I know my B field is this way. It's coming out. So since it's coming out, my current would be running this way through the loop, and so it would come out this side and over here, so it would come into the negative. So when I go this way, it's going to run from positive to negative. Let's see if it matches. So I get a negative voltage, negative EMF. Yeah. All right. Anyway, you'll do some problems, you'll figure it out. It's not that difficult. Just think of the change in flux. That's what it's going to oppose. So it opposes any change in flux. And this does some cool stuff. So I'll show you in class some cool things the way it plays out. All right, Faraday's law. So we have an induced current. You get a coil up here. So we have a coil, and we know that if we put a change in flux on it, so if I move this thing towards it, I'm going to get a reading on it. This is going to move. Now what we want to do is we want to be able to calculate that. And we calculate it using Faraday's law. So recall that the potential here is referred to as the EMF. So we want to calculate the EMF from the induced current when we move a magnet, or we move the coil, whatever. When we're inducing a current, I guess is the way to say it. So, well, we know that the current is dependent upon EMF. So we know that the EMF is going to be dependent on the change in flux. We've already established that. So the change in flux, which in turn is dependent upon the magnetic field and the area of the coil. It's also dependent on the number of coils. So if I had 2 coils, it would be twice this. And so it's also dependent on the number of coils. And there's one other thing, so that's why I was using this demo, was to show you. So if you watch the needle, I'm going to move it slowly, so we get a little bit. But if I move it quickly, you get a whole bunch. So slow, and then quick. Well, quick, yeah, quick. Slow. Yeah. Okay, so it's dependent upon the velocity, but my velocity, I'm covering the same distance, and so it actually ends up dependent upon the inverse of time. Why the inverse? Because when this gets smaller, this gets bigger. So the less time it takes, the more EMF I'll get. And so then that gives us Faraday's law. So Faraday's law is that the EMF in an induced wire is going to be the change in flux. Sorry, I keep putting M's for magnet. That should be a B. Divided by the change in time. And then the current, because of Lenz's law, it's always opposite the change in flux. So we typically will throw a negative on there. And that's Faraday's law. It's on your equation sheet. We can change that top one too. We could rewrite it, of course, because we know the change in flux is just B dot A. So if you had it in terms of area and the B field, then you could figure out it's the change in this over the change in time. We could figure out the EMF as well. But that's Faraday's law. It's a pretty easy application. The hard part's thinking about the change in flux to figure out the direction of the induced field. All right, that was probably confusing. Sorry for all of this stuff. I was trying to find some other relationship that I hadn't thought about before. But that's it, Lenz's law and Faraday's law.